All right. Good morning, everybody. Let's pick up where we uh, left on Tuesday. So we are talking about chemical bonds. On Tuesday, I showed you the ionic bond. Ionic bonding involves an atom that wants to lose one electron and an atom that wants to gain electrons. Remember that atoms will lose or gain electrons to achieve stability. And stability means 8 electrons in the valence shell, because that's the configuration of the noble gases. Okay, so any element will react to achieve 8 electrons in the valence shell. So today I would like to present you the other kind of chemical bonding, and that's called covalent bond. So let's see where we left on Tuesday. So that was the last thing I showed you. Hydrogen, oxygen, and nitrogen, they are found in nature as gases that have molecular formula H2, O2, and N2 respectively. So if we look at hydrogen, oxygen, and nitrogen, all of them need to get electrons to achieve stability. How is that possible that two elements that need to get electrons to achieve stability can bond to form a stable compound? So let's start with the hydrogen. It's the simplest case in the periodic table. Remember that hydrogen has only one electron in the valence shell, and it is one of the exceptions for stability. Hydrogen, helium, lithium, and beryllium, they only need 2 electrons in the valence shell to achieve stability. That's called the duet rule. Okay, so let's switch screens here. Okay, so we know that hydrogen is found in nature as a very stable compound, H2, and we know that each hydrogen atom needs to get 1 electron to achieve stability. Always, when two or more elements combine and both of them need to get electrons to achieve stability, we are going to form a chemical bond called covalent bond. What is the idea in the covalent bond? So imagine here that we have a hydrogen atom isolated. The lone electron that hydrogen has, I'm going to represent by a dot. And we have another hydrogen atom that also has a lone electron that I'm representing here by a dot. One hydrogen needs to get 1 electron to achieve stability, and the other one also needs to get 1 electron to achieve stability. One hydrogen looks to the other one and has the brilliant idea to, instead of losing and gaining electrons, why don't we share what we have? In sharing what they have, they are going to combine, get really close together, and now both of the electrons are shared between the two atoms. And to indicate that the electrons are being shared, we are going to highlight with a circle around the pair being shared. Now, the electrons belong to both hydrogens. So if we look at this hydrogen, now we have 1, 2. So remember that the electrons in the bond belongs to both. This hydrogen now has 2 electrons, and this one has 2 electrons as well, because the pair of electrons is being shared. And that's how the covalent bond works. That's how sharing electrons will yield stability. This representation using dots is called Lewis notation. We can also represent a covalent bond by a solid trace. When there is only one trace, that's called single bond. And that's how elements that need to get electrons will combine with each other to achieve stability. Remember that always when a pair is being shared, this pair belongs to both atoms and not just one atom anymore. So one very simple way to imagine the covalent bond is by drawing some sort of puzzle pieces. Every time we have a lone electron, that's going to yield a spot that the puzzle can fit another piece. So we can represent hydrogen as only one spot because there is only one lone electron. And the other hydrogen, the same thing. So we have a place that we can fit only one piece. When they combine, forming hydrogen gas, you have a perfect fit. Okay, and then another hydrogen here. And that's called single bonding. So let's talk more about the Lewis notation. And let's give you some examples, and then we will move on to more complex structures. Okay, let's see here. Have to come back here to the other screen. Okay, I will get back to the characteristics later. Surprisingly, we didn't put here. Where is it? Okay, so let's talk a little bit about the Lewis notation. The Lewis notation is very useful when we have covalent bonds. And that kind of notation will represent the valence electrons by dots around the element symbols. So for example, hydrogen, as we saw before, has only one electron. So there is only one dot around the hydrogen. If we move on to helium, now two valence electrons, therefore two dots. If we move on to boron, boron belongs to the group 13. Remember, 13 minus 10 is 3, so only 3 electrons in the valence shell, therefore 3 dots. Okay, so 1, 2, 3. Carbon has 4, 1, 2, 3, and 4. Always try to go around the element symbol first, and then you start pairing electrons. Remember, each lone electron here is a place that another atom can fit as a puzzle piece. Moving on to nitrogen, now we have 5 electrons, 1, 2, 3, 4, and 5. See here that I have a spot that I have a pair of electrons, so this spot will not be able to bond. And we have 3 spots only that have only 1 electron, so these 3 spots can fit as a puzzle piece. So let me draw examples for carbon and oxygen here. So let's move back to the other screen. So let's talk again about carbon. Carbon belongs to the group 14. Therefore, we always need to know the number of valence electrons. We have 4 electrons in the valence shell. The way we will represent the 4 electrons in the valence shell using the Lewis notation is by representing each electron by a dot. So always start from this left position and then go counterclockwise. 1, 2, 3, and 4. Okay. Each spot that has only 1 electron will be able to bond with another element. So imagine that each single spot here that has only 1 electron is a place that we can fit a puzzle piece. So for carbon, you can go up to 4 spots to fit another atom. If we move on to oxygen, now oxygen is from the group 16. Therefore, 6 electrons in the valence. Let's draw the Lewis representation for the oxygen atoms, symbol of the element, and then we will fit 6 electrons, 6 dots around oxygen. So let's start here. 1, 2, 3, 4, let's go 5, and let's go 6. If we have 2 electrons, we will represent this as a flat piece of the puzzle. So that's going to have a flat edge on the left and a flat edge on the bottom. However, the edge on the top will be able to bond because there is only 1 electron over there, and the edge on the far right will also be able to bond. Okay, and that's how oxygen will combine with other elements to achieve stability. Okay, so always try to fit atoms in the puzzle that can be fitted to achieve 8 electrons in the valence shell for all of them. Remember, when you have hydrogen, 2 electrons is enough for stability. So the trick here is that always when you have hydrogen, there always going to be a single bond, okay? And that's going to be enough for hydrogen. Okay, let's see if I have more space here. So let me make some space here. Okay, so we talked about the hydrogen-hydrogen bond. So there is only one pair of electrons being shared, therefore this is called single bond. Now, how is that possible? Two oxygen atoms combine, forming the oxygen gas. We know that oxygen has 6 electrons in the valence shell, and we represented here already. So let's draw the Lewis representation for that. 1, 2, 3, 4, 5, and 6. And let's draw another oxygen here. 1, 2, 3, 4, 5, and 6 electrons as well. Each oxygen needs to get 2 electrons to achieve 8 electrons and therefore stability. So we can do that in 2 different ways. We can bond oxygen in 2 spots here with, for example, hydrogen and achieve stability. However, how can we combine 2 atoms of oxygen in order to achieve 8 electrons for both of them? If we go back to the puzzle, I showed you that we have 2 spots for bonding, and that's one of the possibilities, sorry. What about if I move one of the spots over here? So now we will have some unconventional puzzle piece that has 2 spots for bonding. And that's how oxygen will combine with each other. So they will get closer. Now we have something like that. So I just moved this lone electron over here and this lone electron over here. Now we are going to share one pair, and we can count the number of electrons. 1, 2, 3, 4, 5, and 6. Remember that the shared pair of electrons belongs to both. 6 is still not enough to get to 8. We need one more pair shared, and that's going to be the pair at the bottom here. And we circle them. So imagine here that we have a double slot in this puzzle and also a double slot in the other puzzle. And when they combine, the pieces will fit perfectly together. Here, the other atom over here. Now, in this case, we don't have one single bond, but now we have 2 bonds, okay? So we represent the pair of electrons being shared by a trace. Each pair, one trace. When we have 2 pairs, that's called double bond. And look here, we have 2 pairs of electrons that are not being shared. So I'm going to represent them here. And the pairs that are not being shared, they are called lone pairs. Okay, so covalent bonds involves sharing of electrons. Each pair that's being shared means that the 2 electrons belong now to both atoms that participates in the bond. If we just have one pair being shared, that's called single bond. If we have two pairs being shared, that's now receives the name of double bond. The pair of electrons that are not being shared, they are called lone pairs. Always when we have hydrogen, remember that for hydrogen, only two electrons will be enough to achieve stability. Therefore, hydrogen only makes single bonds. Okay, hydrogen cannot make more than one single bond. Okay, so the most important part, one of the most important parts in this chapter is to learn how to draw Lewis structures when we have covalent bonds. Okay, so I'm going to do some examples together with you, and then we will go from there. So here is the secret. First step is to count the total number of valence electrons, account for charges. If we have positive charges, that means we lost electrons, and if we have negative charges, means we gained electrons. If there is two or more different kinds of atoms, you have to pick who is the central atom. Usually the central atom is the largest atom or the one in the lowest number in the formula. Okay. And then fourth step is to distribute electrons among the atoms to fill the octet. And remember, every time you have hydrogens, that means you can only have a single bond between hydrogen and the central atom, or hydrogen and the neighbor atom. So let's see how that works. So let's start with CH4, methane. Hydrogen, we know that has only one electron in the valence shell. Remember that we are always counting the valence shell here. And carbon belongs to the group 14, therefore 4 electrons in the valence shell. Okay. For CH4, we have 4 atoms of hydrogen, therefore the total number of electrons for all the hydrogen atoms is going to be 1 times 4, which means 4 electrons. Therefore, the total number of electrons for CH4 is 8 electrons. Okay, that's the total number of valence electrons from this molecule. Now what we are going to do is to distribute 8 electrons among all the atoms to achieve stability, to fill the octet. Remember, for hydrogen, 2 electrons is more than enough. Hydrogen will always make single bonds. Okay. Second step, Account for charges. CH4 is a neutral compound, therefore no charges. Third step is to choose the central atom. Hydrogen can never be the central atom because it's a small atom. The central atom is the largest one and usually the atom in the lowest amount in the formula. In this case, we have to decide between carbon or hydrogen for central atom. Here is very easy. Carbon has to be the central atom because hydrogen can never be a central atom. So what we do here now is to put carbon in the center, and let's spread the hydrogens around the carbon. We know that hydrogen can only make single bonds. Therefore, each hydrogen will make a single bond with carbon. A single bond means that a pair of electrons is being shared. And now what we do is to count the electrons for each atom and verify that the octet rule was obeyed. Or for hydrogen, the duet rule was obeyed. Remember that each pair of electrons being shared means that two electrons belong to both atoms. So this hydrogen here on the top has two electrons, therefore it's good to go. This one has also two electrons over here, and two electrons over here. So all the hydrogens are stable. For carbon, 1, 2, 3, 4, 5, 6, 7, 8. So carbon, oops, also achieved 8 electrons in the valence shell. So this is called Lewis representation. So we can represent this structure using some sort of structural formula. The structural formula will draw traces in the spots that there are electrons being shared. So let's spread the hydrogens here. Then 1, 2, 3, and 4. Okay. When there is only one single trace, we call that single bond. Therefore, each hydrogen is making one single bond with carbon, and the carbon atom is making 4 single bonds in total. Okay, so the trick here to figure out one of the tricks to figure out the number of bonds that an atom can make is again to use the puzzle sort of analogy. Okay? So carbon we have 4 electrons in the valence shell. So that means we have 4 spots with single electrons. Every spot that has only a single electron is going to be an edge of the puzzle piece that we can fit another atom. So carbon can make a max of only 4 single bonds. Okay, cannot exceed that. We can always shift the spots to fit pieces to other edges to make double bonds or even triple bonds. Okay, so let's move on. Uh, and I would like to go with you for a second example. So now we have a more complex system here, PCl3. Phosphorus is from the group 15 and chlorine is from the group 17. So you can see that phosphorus needs to get electrons and chlorine needs to get electrons as well. Therefore, when these two atoms combine, they will share electrons. Therefore, there is a covalent bond between phosphorus and chlorine. All right. So the first step is to count the total number of valence electrons. So let's do that. Phosphorus belongs to the group 15. Remember that we only need to know the number of valence electrons. If an element belongs to the group 15, that means it has 5 electrons in the valence shell. And we just have one. Chlorine, on the other hand, belongs to the group 17. Therefore, look at here, 7 electrons in the valence shell. However, we have 3 chlorines in the structure, which means that we have to multiply the number of electrons in the valence shell for chlorine by 3, which brings us to a total number of electrons equals to 21 plus 5. That's going to be 26 electrons. Okay, so we have to distribute 26 electrons among 1 phosphorus and 3 chlorines to achieve stability for everybody. The second step is to account for charges. PCl3 is neutral, therefore no need to account for charges. Third step is to choose the central atom. Remember that the central atom is always the largest atom or the one in the lowest amount in the formula of the compound. In this case, our central atom is going to be phosphorus. Fourth step is to distribute the electrons among the atoms to fill the octet. So what the trick that I will do here is to draw the 3 chlorines around the phosphorus. Okay. And now we start making a single bond between each chlorine and phosphorus. So we will go a single bond here that requires 2 electrons, another single bond here, and that requires 2 more electrons, another single bond here, and that requires 2 more electrons. Therefore, I spent 6 electrons just to bond phosphorus with chlorine. Okay, so let's subtract 6 electrons from the total. So there is still 20 electrons remaining. Of course, neither of the atoms achieved 8 electrons in the valence shell. Therefore, we need to spread more electrons in each atom to get 8 electrons in the valence shell. And here is the trick. We are going to start to fill the octet first for the elements on the outside of the structure. For chlorine, we have 1, 2, 3, 4, 5, 6, 7, and 8. Now that this chlorine achieved stability, we move on to the next one. 1, 2, 3, 4, 5, 6, 7, and 8. 8 electrons here. This is stable. Moving on to the next. 1, 2, 3, 4, 5, 6, 7, and 8. Okay, and this here is stable because now we have 8 electrons as well. And now we look at the central atom. So phosphorus only has 1, 2, 3, 4, 5, and 6 electrons in the valence shell, so therefore it's not stable. And to achieve stability, we add a pair of electrons to the phosphorus atoms. And now we count everything to make sure we didn't go over 26. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26 electrons. Therefore, everybody is stable. Another way to draw this structure, a more elegant way, is to represent the pair of electrons that's been shared by solid traces. And then in this case, we have pair of electrons that are not being shared. So we represent them here as well. And I want you to always do that. And remember, these electrons that are not being shared, they are called lone pairs. And each single trace is called single bond. Okay. So here is another trick. Fluorine, chlorine, bromine, and iodine, they will only make single bonds, okay? Because they have 7 electrons in the valence shell, therefore there is only one spot to bond. If we use the analogy of the puzzle, we have here chlorine, and let's represent the 7 electrons by dots using the Lewis structure. Each side that there is a pair of electrons is going to be a flat edge. So we have flat edge on the top, on the left, and at the bottom. And the edges that have only one electron is the one that will make the connection. So chlorine always makes one single bond. Okay, and you could do the same thing for phosphorus. Okay? One, two, three, four, five. The side that has already two electrons is going to be a flat edge, and the side that has only one electron is going to be the side that we can fit other atoms. So therefore, phosphorus will make a max of three single bonds in most of the cases. Okay, let's see another example here. Let's try to draw the Lewis structure for NH3. Again here, nitrogen needs to get electrons and hydrogen needs to get electrons to achieve stability. Therefore, the kind of bond formed between nitrogen and oxygen is called covalent bond. Okay, the atoms will combine, sharing a pair of electrons to achieve stability. Okay, so let's give you a couple minutes and let's see if you can come up with a solution, and then after that I will do with you. All right, so every time we have a covalent compound, now the electrons belong to the whole molecule as one unit, okay? And that's why we count the total number of valence electrons. We are going to distribute the electrons among the atoms to fill the octet for all the atoms in the structure. Remember, if we have hydrogen, then two electrons for hydrogen is more than enough. Therefore, hydrogen will always make single bonds, no more than that. Okay, so let's start counting electrons. Hydrogen has only one electron in the valence shell. However, we have three hydrogens in the structure, which will yield a total of 3 electrons. So all the hydrogens are contributing with 3 electrons for the molecule. Nitrogen belongs to the group 15. Therefore, 5 electrons in the valence shell, and that's the contribution from the nitrogen. There is only one, therefore that's it, which will yield a total number of electrons equals to 8. So we have 8 electrons in total to distribute among the atoms to make everybody happy. There is no charge in this molecule, therefore we don't have to subtract or add electrons. The next step is to choose the central atom. Remember, hydrogen can never be a central atom. Therefore, the only option here is nitrogen. And then we are going to distribute the electrons among all the atoms to fill the octet. So the strategy here is to spread the hydrogens around the nitrogen. Now, nitrogen and hydrogen will share a pair of electrons. So that's a good starting point. So share one here, share one here, another pair of electrons shared here as well. Okay, and now we count the number of electrons and verify if everybody in the structure is happy. Remember, each pair of electrons that is being shared belongs to both of the atoms. So let's start with the hydrogen on the most left side here. We have 2 electrons for this hydrogen, so that's enough to achieve stability for this hydrogen. The one at the bottom, 2 electrons, that's good enough. And then the one on the right, 2 electrons, so that's good for the hydrogens. So all the hydrogens are happy. However, nitrogen has only 1, 2, 3, 4, 5, and 6 electrons. That's not enough. We have a total of 8 electrons. 6 were spent to just make the bonds, so we still have 2 electrons left. We will toss to the nitrogen. Now nitrogen has 6, 7, and 8 electrons. Okay, and then nitrogen is stable as well. Another way to draw this structure is using traces to represent the covalent bonds. So 1, 2, and 3. And I always want you to draw the pairs that are not being shared. Remember, the pairs that are not being shared are called lone pair. Okay? And each solid trace is called single bond. Always remember, hydrogen will only make one single bond, cannot make more than that. If you use the puzzle analogy to figure out the max number of bonds of an atom, you will get to a similar conclusion. So nitrogen has 5 electrons, one, two, three, four, 5. Each edge that has a pair of electrons is going to be a flat edge, and each edge that has only one electron will be a spot that a covalent bond can be made. Therefore, nitrogen will make a maximum of 3 single bonds. And for hydrogen, only one electron. So here is very simple. Hydrogen has only one spot that is possible to bond. And therefore, that's the structure of NH3. We haven't seen any compound that has charges. However, if you have a positive charge, it needs to subtract electrons, okay, from the total. And if you have a negative charge, you need to add electrons from the total. For example, if we have NH4 plus, we are going to have a total number of electrons equals to 5 from the nitrogen plus 4 times 1 electron from the hydrogen. This comes from nitrogen. This comes from hydrogen. And because you have 1 plus charge, that means you lost 1 electron. Okay. So for this species, for example, you would have a total of 8 electrons to distribute among all the atoms. Okay, so the analogy of the puzzle pieces is a very simple one and explains a small part of all the cases. Is a nice guide to try to figure out things, but do not stick to it to everything, okay? Because there is always exceptions. All right, and let's do one more example, and then I will show you the Clark's rule. Okay, last example here is the structure of CO2. Again, we are combining two or more elements that need to get electrons to achieve stability. Therefore, the kind of bond formed is called covalent bond. In this case, we have carbon dioxide, CO2. Let's start here counting the total number of valence electrons. Oxygen belongs to the group 16. Therefore, 6 electrons in the valence shell. However, we have 2 oxygens in the structure. Therefore, the total contribution of oxygen for the molecule is 12. Carbon is from the group 14. Therefore, 4 electrons in the valence shell. There is only one. Therefore, that's it. Which means we have a total number of electrons in this compound equals to 16 electrons. Okay, so we are going to use all the 16 electrons to make covalent bonds and make sure all the atoms are happy. All the atoms achieve 8 electrons in the valence shell. There is no charge in this molecule. We don't need to add or subtract anything. Next step is to choose the central atom. Central atom here is going to be the largest one or the one in the lowest amount in the formula, usually. This case is very simple. It has to be the carbon. And now we are going to distribute the 16 electrons among all the atoms to fill the octet. So let's put each hydrogen next to the carbon atom. Remember that each oxygen next to the carbon atom, each oxygen is from the group 16, therefore it needs to get 2 electrons to achieve stability. Okay, so we always start with single bonds between the atoms to connect them. So that's always the starting point. So just to make a single bond, 4 electrons were spent. We still have 12 to distribute. However, if oxygen needs to get 2 electrons to achieve stability, each single bond will bring an extra 1 electron. So that's not enough. Therefore, oxygen will make another extra bond with carbon. So now we are bringing 2 electrons to the oxygen, and that will be enough. And then the same case on the other side. Now, for the chemical bonds, we spent 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. Therefore, we still have 8 electrons to be distributed. Whatever is left is going to fill first the octet from the atoms on the outside, and if there is something left, you move on to the central atom. Oxygen has 1, 2, 3, 4 from the chemical bonds, 5, 6, 7, and 8. Okay. and then 5, 6, 7, and 8. So now we spent all the 8 electrons that were left. Therefore, there is nothing left for carbon. Now let's see if everybody's happy in the structure. Starting from the oxygen on the left, 1, 2, 3, 4, 5, 6, 7, 8. This is good to go. The other oxygen on the right side, 1, 2, 3, 4, 5, 6, 7, 8. So remember that each covalent bond counts as 2 electrons, and these 2 electrons belong to both atoms. And let's check if carbon is good. 1, 2, 3, 4, 5, 6, 7, and 8. So that's also good. Another way to draw this structure is by using traces to represent each pair of electrons that is being shared. And I always want you to draw the lone pairs in the structure. Now that we have instead only a single trace between carbon and oxygen, but a double trace, we call this kind of bond as double bond. And remember, each pair of electrons that's not being shared is called lone pair. Okay, so one of the common questions that I usually get in this structure is that why do I need to have a double bond between carbon and oxygen and not a single bond? Well, let's draw the structure and let's see what we get. Okay, single bond here, single bond here, oxygen and oxygen. So just to make the bonds, we spent 4 electrons. If we have a total of 16, that means we have uh, 12 electrons left. So we are going to start filling the octet from the atoms on the outside. 1, 2 electrons for oxygen, 3, 4, 5, 6, 7, and 8. And then we move on to the other oxygen on the other side. 1, 2, 3, 4, 5, 6, 7, and 8. And then with that, we spent all the 16 electrons just to draw this structure. Now let's see if all the atoms are happy in the structure, because all of them need to be happy. Oxygen on the left, 1, 2, 3, 4, 5, 6, 7, and 8. That's good to go. The other oxygen is also good to go. However, look at the carbon atom. Carbon only has 1, 2, 3, and 4 electrons. So it still needs to get 4 more to achieve stability. And that's why this structure is not correct. And we need the double bonds there to make sure the carbon is also stable. The carbon also has 8 electrons. And remember, each bond always has 2 electrons, and the 2 electrons belong to both atoms. So 1, 2, 3, 4, 5, 6, 7, 8. So when we have 2 double bonds, we have 8 electrons for the carbon. And that's how this molecule is going to be stable. So always pay attention when you have single bonds and when you have double bonds. You will always start making single bonds and see what happens. And then you go from there. If a double bond is needed, then just add a double bond. The tricks here. Hydrogen always make single bonds. Fluorine, chlorine, bromine, and iodine always make single bonds as well. Okay, so there is a trick to figure out if we only have single bonds or if we have double bonds or even triple bonds. And that is the Clark's rule. It's a very simple rule. There is some sort of just empirical rule, so there is nothing scientific backing up, but it works for all the structures, and it's very surprising actually. So what you are going to do is to compare a number with the number of valence electrons, okay? So we have a number that we are going to call x, and x is equals to 6 times the number of non-hydrogen atoms plus 2. And we are going to compare x with the number of valence electrons. If x is equals to the number of valence electrons, then only single bonds. If x minus the number of valence electrons is equals to 2, then you need one double bond. And if x minus the number of valence electrons equals to 4, then you need two double bonds or one triple bond. So let's see how the Clark's rule works. Let's start with the NH3 structure. So we already know the structure of NH3. So let's see how we would use the Clark's rule to figure out uh, if there is single bonds, double bonds, or even triple bonds in this structure. So we are going to start calculating X. That's going to be 6 times the number of non-hydrogen atoms plus 2. In the NH3 structure, we just have one atom that's non-hydrogen. Therefore, 6 times 1 plus 2, which is equals to 8. And now we are going to compare 8 with the number of valence electrons. Let me draw here valence electrons. We have 5 from the nitrogen plus 3 times 1 from all the hydrogens, which yields 8 as well. So in this case, X is equals to the number of valence electrons. Therefore, only single bonds in the structure. And we know that this is true because this is the formula, the structural formula of NH3, ammonia. Okay? We know that there are only single bonds. Now let's do the same thing for CO2. So before we draw the structure of CO2, we can use the Clark's rule to know in advance if we need double bonds, triple bonds, or if only single bonds will be present. First step is to calculate X, 6 times N plus 2. Remember that N is the number of non-hydrogen atoms. In this case, all of the three are non-hydrogen. 6 times 3 is 18, plus 2, that's 20. And we are going to compare this number with the number of valence electrons. We have 4 for the carbon, plus 2 times 6 for the oxygens, and that's going to yield 16. In this case, X is different from the number of valence electrons, so we are going to subtract X from the valence electrons, which is equals to 20 minus 16. That's going to yield number 4. 4, you are here in the third case. In this structure, you will need 2 double bonds or 1 triple bond. Okay? So how do you decide between the two? Draw the two possibilities and see which one will get 8 electrons for all the atoms. We know that CO2 has 2 double bonds. Okay? And that's how the Clark's rule can help you drawing Lewis structure. Start with the Clark's rule, then you have an idea if there are single, double, or triple bonds. Then remember, hydrogen will always make single bonds, and all the elements from the group 17 will always make single bonds as well. With that, that's a very good starting point. You pick the central atom, count the total number of electrons, and start making single bonds. Then, after the bonds are made, you start filling the octet from the elements on the outside. If electrons are still left, you dump them to the central atom. And that's how you draw Lewis structures for covalent compounds. And I think that should be enough for today, and I will see you in 2 weeks. Hope you have a good break.
Thank you, Professor.
Thank you. Have a good break.
Thank you.
Thank you. Have a good break.